All right, welcome back here. Goal right now is to present the equations of motion. Yes, this is going to be a super important video that you're going to want to follow along with. I'm going to switch over to the document camera and show you the equations I want you to copy down into your notes. Okay, so your textbook has some kinematic equations. These are just the equations of motion. They're the same ones. I think these ones are a little more user-friendly, and I'll walk you through them. There's 4 of these equations, so you're going to want to start by copying these down. You can see at the top it says that these are for constant acceleration, so that's really important. If the acceleration is not constant, these are not valid equations. So let's start by talking about the variables here. We've got delta x, which is our position variable. We have final velocity, initial velocity, time, and acceleration. So we have 5 possible variables that are related by these equations. And I have them numbered as equation 1, equation 2, equation number 3, and equation number 4. And those relate the variables of motion that we might be interested in. And you can see I've created a kind of a little data table here to help guide you as to which equation to use based on the problem that you are working. So at the top here I have equation 1, 2, 3, and 4. And then across the side I've got the variables: my position, initial velocity, final velocity, acceleration, and then time. And you can see that each equation relates only 4 of these variables at a time. And what that means is, if you look at this first row here, I have check, x, check, check. Well, what that means is equation number 2 does not include the variable position. So if we go back and look at equation 2, you can see how there's no delta x term in that equation. So when selecting which equation to use, you can go off of the variable that's not included. And I'll explain how to use that in an example here in just a moment. So basically we have these 4 equations. You've got 5 variables. You got to have at least 4 of them to solve a kinematics problem, and then 3 of them, and you'll solve for the 4th variable, and then we generally don't need the 5th variable to solve the problem. So let's take a look at number 24. It's one of the problems I assigned this week, and I'll walk you through how to solve that problem. So on number 24, we have, I'll just read you the situation here. A race car traveling on a straight racetrack with a forward velocity 44 meters per second and slows at a constant rate to a velocity of 22 meters per second over a time interval of 11 seconds. How far does it move during this time? So what I did was I wrote out, and this is what you should do, what do we know in this problem? So in this first unit, there's some really important problem-solving strategies. And begin by writing what you know, writing what you're looking for, and then we'll put an X over the variable that we don't really care about for this problem. So here was my initial velocity value. It's a positive value. That's important. My final velocity value was 22 meters per second. Also, I'm still positive. I'm still going to the right. It just means I've hit the brakes, basically, and I've slowed down. And they tell us in the problem that the acceleration is constant, but they don't tell us what it is. And then our time interval that this braking takes place over is 11 seconds. And ultimately, we're being asked for, well, what is the distance that the car covers during this time interval? So once I've listed my 3 things that I know, what I'm looking for, and then what I don't care about. I'll take a look at that chart. And so the one I don't care about was acceleration. And so that's going to guide me to the equation that will make the most sense to use. So you can see, here's my acceleration variable. Equation 1 does not have acceleration in it. So that means I'm going to want to use equation 1, which is up here. Why? Because it doesn't have an a term in it. I don't really care about it. I've got my final velocity, my initial velocity, and my time, and we're looking for how far does the car go in that time, which is our position. So equation 1 is going to get us there. So I plugged in those numbers here. My delta x, my position, is equal to my final velocity plus my initial velocity divided by 2. So really it's the average velocity multiplied by the time interval that we're moving at that average velocity. So 22 final velocity plus 44 initial velocity divided by 2 multiplied by 11 seconds gives us an answer of 363 meters. Now the correct sig figs, we would look back at the problem. All of these values have 2 digits, so I wouldn't want to express 3. I'd have to round to 2. So my correct answer here would be 360 meters, and that's what you should see on Slater if you check this problem. Okay? I'll do one more example this week. Okay, here's another one of your problems for the week. This is number 41, letter A. A construction worker accidentally drops a brick from a scaffold. What is the velocity of the brick after 4 seconds? So as we talked about, we're going to begin with writing, well, what do we know and what are we looking for? Well, we're being asked velocity after 4 seconds, so that's going to be our final velocity, is our question mark. Our time interval, 4 seconds. And then it's like, I don't really know much else. I thought we had to know 3 things and solve for a 4th. Well, there's some implied things when dealing with problems involving free fall. We are always going to know the acceleration value is negative 9.8 meters per second squared. Why? Because gravity is a constant value. Make sure you write the negative in there, otherwise you'll get it wrong. We've got to know something else. I have 2 pieces of information. There's a piece of implied information in the problem. It says a construction worker drops a brick. So the brick initial velocity was 0. And then our other variable that we haven't yet talked about is our position. We might say position as delta y in this case because it's going to be vertical displacement. And do we care about that? Well, we're not told it. It just says it's a high scaffold. So no, we're going to ignore vertical displacement for this part. We've got 3 things here we can solve for the 4th. Let's go back to the equations of motion. The one we don't care about is what guides us. So our displacement is not included in equation number 2. So equation 2 was this. I'll copy that down. Equation 2, final velocity equals initial velocity plus acceleration times time. I write my t's with a little curve so it's different than a plus. Okay, so let's plug in the values that we know. We know the VF is what we're looking for. Our initial velocity is 0. Our acceleration is negative 9.8. And our time was 4 seconds. So take a moment to work that problem. All right, there it is. 9.8 times 4, 39.2 meters per second. And make sure you write the negative value. That tells us the velocity is going down. Some of you might be tempted to think, doesn't it stop when it hits the ground? And in these sorts of problems, we stop our motion at the moment before impact. Collisions involve some separate physics involving momentum, which we'll get to later in the course. So what about significant figures here? The book answer says 39 meters per second. If we look back at the problem, we had our time value was actually given as 4.0. So they did that to show us this is two significant figures. Remember that 0 after the decimal is significant because there is a decimal in the number. Therefore, I would round this to just a negative 39 meters per second, or I could just say 39 meters per second down. That works for me too. Okay, hopefully these examples will help you. The problems just got a little bit harder this week, so I'm expecting you guys to be asking some good questions in class. All right, good luck.